Hi there, and welcome to this lesson on Further Pure Mathematics 2. And in this lesson, we'll be looking at how you solve second-order, non-homogeneous differential equations with constant coefficients. Now, what are those exactly? Well, they're differential equations of this form. Second order means that we've got d2y by dx squared involved in the equation. Non-homogeneous, because we now have a function of x on the right-hand side, not just 0. And the constant coefficients are the values a, b, and c here, which are all just constants. Sometimes in terms of notation, you might see it written down like this, which is quite similar to what you see in function language when you have f double dashed of x. There's two steps to solving these. The first step is exactly the same as we did in the last lesson. We begin by imagining the differential equation was equal to 0, and we solve that in the normal way. And the solution we obtained has a special name. It's called the complementary function, sometimes written as CF, or y with a little c. And then we have to consider this function on the right-hand side. And we find a particular integral which has the same general form as this function. We'll talk more about that in a moment. Once we've found the complementary function and the particular integral, then we just add those two things together. And that gives us the general solution. So you may see it written down like this. The general solution is the complementary function plus the particular integral, or just y equals yc plus yp. Now, coming back to the particular integral, this function here, we need to find a particular integral which has the same general form as that. Now, what does that mean? It means, for instance, if this function was an exponential function, ae to the alpha x, the particular integral would be an exponential function of the same general form. That means the power will be the same. So if we've got alpha x here, the particular integral will also have exactly the same power. The only thing that changes is the constant on the front, and we won't know what that is, so you just choose any letter you like. If you had a trig function, and that means either cos some multiple of x or sine some multiple of x, then the particular integral is the general trig function. But you've got to be careful here. The general trig function has to include both possibilities. So the particular integral will be both a multiple of cos alpha x plus a multiple of sine alpha x. If we have a polynomial, then a particular integral is the polynomial of exactly the same degree. So if it's a quadratic for f of x, then the particular integral will be the general quadratic. If it's a cubic, the particular integral would be the general cubic, and so on. Now, once we've found the general form of the particular integral, we then differentiate it, and differentiate it a second time to get dy by dx and d2y by dx squared, and then we substitute all of these three things, y, dy by dx, and d2y by dx squared, into the original differential equation. And we solve an equation then in order to find the value of the constants a, b, and c, a, b, or whatever constants you've chosen to use. Okay, let's have a look at how this works out in practice. So if you had to find the general solution of d2y by dx squared minus dy by dx minus 6y equals 2e to the 2x. You find the complementary function by solving when this is equal to 0, and then you choose a particular integral y equals ae to the 2x. Differentiate it once, differentiate a second time, substitute those into the equation, and move on from there. Now, I'll let you have a go at doing this yourself first. So pause the video, have a go, and then come back to me again when you're ready. Okay, let's have a look. So the auxiliary equation is n squared minus n minus 6 equals 0. That factorizes into n minus 3 times n plus 2 equals 0, which gives us two solutions, plus 3 and minus 2. So the discriminant's positive. The auxiliary equation's got two distinct real roots, which means this will be the general form of the complementary function, ae to the n1x plus be to the n2x. Substituting in these two values, 3 and minus 2, that gives us the complementary function, ae to the 3x plus be to the minus 2x. Now we need to look at this function here on the right-hand side, and we need to take the general form of that. Well, the general form is ae to the 2x. That means the particular integral will be y equals ae to the 2x. Differentiating that gives us this. Differentiating the second time gives us this. And then substituting these three things into the original equation will give us this. Tidying that up a little gives us minus 4a to the 2x equals 2e to the 2x, which means that minus 4a must equal 2 and a must equal minus a half. That means that the particular integral is y equals minus a half e to the 2x. We already worked out the complementary function, which was a to the 3x plus b to the minus 2x, and the general solution is just those two things added together. So the general solution is y equals a to the 3x plus b to the minus 2x minus a half e to the 2x. Okay, example 2, same idea, but this time the function on the right-hand side is a quadratic. Be careful, there's no term in x here, but when we do the particular integral, we do need to the general quadratic. And the general quadratic is ax squared plus bx plus c. Aside from that, it's the same method as the previous example. Okay, have a go, pause the video, and come back to me when you're ready. Let's have a look. This time, the auxiliary equation is n squared minus 4n plus 5 equals 0. That doesn't factorize. The discriminant is negative. Using the quadratic formula, if we solve that, we'll get two complex roots. N equals 2 plus or minus I. So as we said, in this case, the discriminant is negative. We have two complex roots, and the complementary function will have this form here. E to the real part of the solution times by x, and then you've got cos and sine times by the imaginary part times by x. So the complementary function will be e to the 2x times by a cos 1x plus b sine 1x. The function on the right-hand side is a quadratic. The general form of this is the general quadratic, ax squared plus bx plus c, which means the particular integral has that form. Differentiating that gives us 2ax plus b. Differentiating a second time gives us just 2a. Substituting these three things into the original differential equation gives us this. Multiplying out the brackets will give us that, and then we'll collect together the terms. So we've got 5ax squared, that many x's, that's the constant, and on the right-hand side we haven't done anything. And the easiest way forwards from here is just to equate the coefficients of the three terms. So first of all, equating the coefficients of the x squareds means that 5a must equal 25, which means that a is equal to 5. Equating the coefficients of the x's gives us 5b minus 8a is equal to 0, because there are no x's on the right-hand side. A is 5, so that means 5b minus 40 equals 0, which means that 5b is 40 and b is equal to 8. That's what we've done so far. And lastly, the two constants must be the same as each other, which means 2a minus 4b plus 5c equals minus 7. Substituting the values in for a and b gives us 10 minus 32 plus 5c is minus 7, which gives us 5c is 15 and c is equal to 3. So we found the values a, b, and c in the particular integral, so we can now write down that the particular integral is yp is 5x squared plus 8x plus 3. The complementary function we've already found, and that is e to the 2x into a cos x plus b sine x. And the general solution is just those two things added together, which gives us this. Okay, example 3. Now, example 3 is a little bit more tricky. When we have a trig function, you just have to walk carefully, because the particular integral has to include both cos and sine. So it'll be y equals a cos x plus b sine x. But also, once we've done that and got the general solution, we'll then be able to find a particular solution and find the value of the other two constants, because we've been told that when x is 0, y is 1, and when x is 0, dy by dx is also equal to 0. So using these boundary conditions, we'll be able to find the values of the other two constants in the general solution. This is quite a long question. I'll let you have a go at it yourself first. So pause the video and come back to me again when you're ready. Okay, the starting point is the auxiliary equation, n squared plus 2n plus 2 equals 0. Once again, the discriminant is negative. Solving this using the quadratic formula will give us two complex roots, -1 plus or minus I. When we have complex roots, the complementary function has this general form. Substituting in the values for n1 and n2 gives us a complementary function of e to the minus x times by a cos 1x plus b sine 1x. Now the function on the right-hand side is a trig function, and as we said, if you have a trig function, the general form of that is a cos x plus b sine x. We need to include both things. So that'll be the particular integral. Differentiating that gives us this. Differentiate it a second time gives us this. And then, that's where we've got so far. Substituting those into the original differential equation will give us that, which is equal to 5 cos x on the right-hand side. Now, tidying things up, collecting together the terms in sine and cos will give us that. And a bit like on the last question, we can then equate the coefficients of sine x and cos x. So equating the coefficients of sine x gives us b minus 2a is equal to 0, because there are no sine x's on the right-hand side. And a plus 2b is equal to 5. That gives us a pair of simultaneous equations to solve. I'll let you solve those yourself, but you get the solutions a equals 1 and b equals 2. So the particular integral is yp is equal to 1 cos x plus 2 sine x. That's the complementary function, that's the particular integral. The general solution is adding those two things together. Now this time that isn't the end of the question. This time we've been given extra information, boundary conditions, and those boundary conditions will allow us to find the values of a in front of the cos x and b in front of the sine x. First of all, substituting in that when x equals 0, y equals 1, we're just substituting those into the general solution. That gives us this. Now, e to the power of 0 is 1. Cosine of 0 is 1. Sine of 0 is 0. So that very quickly simplifies to 1 equals a plus 1, which means that a is equal to 0. Now, the easiest thing to do is to just immediately change the general solution. We know that a is 0, so the general solution becomes y equals be to the minus x sine x plus cos x plus 2 sine x. The second boundary condition is that x equals 0 when dy by dx is equal to 0. Well, differentiating that would give us this. And now we can substitute in that boundary condition. So dy by dx is 0 when x is 0 gives us that. Again, things simplify greatly. E to the 0 is 1, cos 0 is 1, sine of 0 is 0. So that all very quickly simplifies to 0 equals b plus 2, which means that b must equal minus 2. So we found a, we found b, we can substitute those in, and that gives us the particular solution. Y is equal to minus 2 e to the minus x sine x plus cos x plus 2 sine x. Now we'll just have a few moments to think a little bit more about particular integrals. Now it really depends on which course you're doing, but some courses ask you to go one step further with particular integrals. We said already that if you've got the differential function is equal to f of x, then we just find a particular integral with the same form as f of x. That works fine as long as the complementary function does not have a term which is exactly the same form as f of x. If the complementary function itself has the same form as f of x, then things can get a little bit more fiddly. What it normally means is that you've got to multiply whatever you'd have normally as the particular integral by x. And just multiplying it by x normally does the job and gets you there. You'd realize that you have a problem on these questions when you do all the normal stuff with a particular integral and then find out that you can't find it. You have problems with the constants. Either the whole thing is equal to 0 or you get something contradictory, but you just can't find the particular integral using the normal method. Okay, we'll go through the three most common cases. So first of all, if you have an exponential function where a and lambda here are constants, first of all, if the complementary function doesn't contain a term of exactly the same form as that, either a e to the lambda x or actually alpha x e to the lambda x, then what we just did is fine. And the particular integral will have the form yp equals ae to the lambda x. However, if the complementary function contains a term of the form alpha e to the lambda x, then the particular integral will need a multiple of x in it as well. So the particular integral will have the form a times x e to the lambda x. And if the complementary function actually contains a term of that form, ax e to the lambda x, then you go one power up. The particular integral will be of the form yp equals ax squared e to the lambda x. So that's if this is an exponential function. If it's a trig function, either a cos lambda x or b sine lambda x. Again, if the complementary function doesn't contain any terms of the form a cos lambda x or b sine lambda x, then what we did before is fine. The particular integral will have the form yp equals a cos lambda x plus b sine lambda x. However, if yc is of the form a cos lambda x plus b sine lambda x, there are two possibilities. First of all, if the function on the right-hand side is a cos lambda x, then the particular integral will be yp equals ax times by sine lambda x. And the other way around, if you have a sine lambda x for the function on the right-hand side, then the particular integral will be ax cos lambda x. With polynomials, if f of x is a polynomial of degree n, now there is an issue, but only if this term here is equal to 0. So normally you're fine and you just say the particular integral is a polynomial of exactly the same order. If it's a quadratic, you do a quadratic. But there is a special case, and the special case is if the original differential equation has got no y term, which means that c is equal to 0 and this term just doesn't exist at all. Now it turns out that if that's the case, for the particular integral yp, you have to add an extra term on, so an extra power of x. So rather than just being the general polynomial of degree n, you'd have to use the general polynomial of degree n plus 1. Okay, that does get us to the end of this lesson. If you've got the textbook, then there are two exercises that you could have a go at. Exercise 6b and exercise 6c on pages 114 and 117. Thank you very much for listening, and cheerio.